Okay, and yeah, sorry for the interruption. And I think the streaming should be back on. And anyway, let's go back to this example of time expansion. Okay, so we have this example of time expansion and showing that. So here we have our signal, which is this block signal is block signal between -2 and 2, and we had before that its frequency domain wave will be the sine over sine function. Once again, it has period 2 pi, and because this is phi spikes here, this is a phi non-zero value here, and so this thing also have basically phi maximum or the minimum per period. And I guess that doesn't make sense. Yeah, it makes a bit of sense. Okay, 1, 2, 3, 4, 5. Okay, and anyway, and then we see that when we stretch out the signal, and then we'll squeeze in the frequency domain signal. So we will stretch out the time domain signal by a factor of 2. Then we'll squeeze in the frequency domain signal by a factor of 2, and we see that instead of one period of this up down up down up down up, then you have two period of 2 pi. Sorry, then you have so this is squeezing by a factor of 2. So between 0 and 2 pi, you have two of those shapes. This is up down up, and then the up down up. Okay, and yeah. So and then we'll see that we stretch out further. So we stretch out the time domain signal by a factor of 3. Then the frequency domain signal will be squeezing by a factor of 3. And so you see that the same signal will repeat itself 3 times between this one period of 2 pi. And but also you see that the squeezing signal in the frequency domain, because you always squeezing by integer vector, 2 pi will always be a period of it. Okay, so this x sub 2 of e to a j omega is a period of pi, but 2 pi is still a period, and this thing has a period of 2 pi divided by 3, and 2 pi is still a period. Fundamental period of 2 pi divided by 3, but 2 pi is still a period, etc. Yeah. So things are working out nicely. Okay. Then we go to the next example to calculate the Fourier transform of this signal. Okay. So the signal is plotted here. So if it has a non-zero value only from 0 to 9, and it is 1, 2, 1, 2, 1, 2 between 0 and 9. Okay. And we try to use all the property we talked about to give the Fourier transform of this thing. So basically, we will try to start with this signal and get the Fourier transform of this signal with the properties. Okay, so the signal is this block signal. Okay, and we get this by first writing this 1, 2, 1, 2, 1, 2 signal as a linear combination of a two stretch out signal. Okay, so we say we can have this 1 of n, which will be a time shift of j of n. This block signal we call j of n. So we start with 1 of n is this 1, 1, 1, 1, 1 between 0 and 4. And if you stretch it out, it will become 1, 1, 1, 1, 1, 1, between 0 to 8. And then you put then you multiply this by 2 and the time shift by 1, and it will be this 2, 2, 2, 2, 2 between 1 and 9. Okay, and then you add together your y2 of n and the 2y sub 2 of n minus 1, then you get back to your 1, 2, 1, 2, 1, 2 signal. Okay, so we see that x2 of n is y2 of n plus 2y2 of n minus 1, where y2 is 1 of n stretched out by a factor of 2. Okay. And so now we see that everything is expressed as some form of y of n, then we now want to get the Fourier transform of y of n to start getting all those things. Okay? And as we say, we get y of n as a time shift over g of n, where g of n is 1, 1, 1, 1 from minus 2 to 2. So y2 of n is just g of n minus 2. G of n divided by 2. Okay? And g of n is this rectangular pose, and we have calculated the Fourier transform of the rectangular pose as the sine over sine. Okay? So g of n is the Fourier transform is sine phi omega over 2 plus sine omega over 2. And then you get the HR time shift, so you get this HR using a time shift property, you get this HR e to the minus j2 omega. Okay, so y of this big Y is e to the minus j2 omega. Then this big G factor, this is sine phi omega over 2 over sine omega over 2. Okay, and so we get big Y, and then big Y, then we can get big Y sub 2. Okay, so big Y sub 2 is big Y, but with 2 times with 2 on every omega. So this 2 omega become 4 omega, and this 5 omega over 2 become 5 omega, and this omega 2 become omega. And yeah, so this is property, and then we use once again a time shift and multiply and just a linear multiplication. So these 2 give you HR2 on the Fourier transform, and then shift by minus 1, then you get HR e to the minus j omega. So you get total e to the minus j phi omega on the Fourier transform this y sub 2 over minus 1. Okay. Sorry, auto battery. Okay, so now we get all our components. So we have a Fourier transform of y sub 2 and the Fourier transform of 2y sub 2 over minus 1, and we add them together. That's a Fourier transform of your x over n. So your big X is e to the minus e to the minus j4 omega, and those HR factor. So 1 plus 2 and the HR e to the minus j omega, and then you have those sine phi omega over omega. Okay. So this is x over e to the j omega without doing the integration, without doing the summation. Okay. So yeah, so you have this quite complicated x over n. Then we see that with this time stretching property, time expansion property, and time expansion property, and time shift and time shift property, and linearity, then we can get it just from this Fourier transform of block signal. Okay, so that's the end result. Any question? If not, we'll go to talk about next property. So this is difference in frequency property. Okay, and you can derive pretty easy. Okay, differentiation in frequency. Okay, so we think about remember the frequency domain signal is a continuous signal, so we can do a differentiation and see what happened to the corresponding time domain signal, and you can just take this equation and do differentiation on omega on both sides. Then you see on this side you just get HR minus jn. So because it only depends on omega, is this e to the minus j omega, you do differentiation, you get a minus jn. Okay? And then you move things around a little bit, then you see that you want, so you see the Fourier transform of the big X, the omega, is this minus jn x over n, okay? Because you get a minus jn. And you move things around a little bit, then you see x over n will Fourier transform to j the big X, the omega, okay? And this property will be useful when we do partial fraction expansion on the later property of convolution. Okay, and yeah, and then the next property we talk about is the Parseval's relation. So Parseval's relation, as always, says that energy in time domain equal to energy in frequency domain. and with some constant sometimes. So the constant now is you get the h1/2 on this frequency domain energy. So time domain energy is the summation over everything squared, and the frequency domain energy, because the frequency domain is a period with period 2 is periodic with period 2 so you only integrate over interval 2 and then you divide by this 2 Okay. And then here we also have a more general form. I think we have done your homework that you derive this more general form in some other Fourier transform. Yeah, you can also have this more general form of possible relationship, where instead of just something square, you have basically the inner product between a signal of x and y. Then you have this integration of the product of x and y. Okay. Integration of the product between big X and Y star, which is also like an inner product between big X and big Y star, big Y. Inner product between big X and big Y. Okay, and yeah, so now we go to some example that test you on all the properties and try to see how people answer it. So we have Fourier the spectrum of some signal. Here is its amplitude look like this, and its angle look like this, and we plot it between -pi and pi. And again, it should be a periodic signal, so outside of -pi and pi, it should just repeat itself. And so its amplitude look like this. It has a funny shape, and its angle is like this. It's just a straight line with slope 2. And so now we have 4 questions here, and we can try to test people that actually come to class. So is x of n a periodic signal? Is a real signal? Is an even signal? And does it have a finite energy? Okay. And so first question, let's try to test. Those are all yes no question. So is x of n a periodic signal? If you think it's periodic, raise your hand. And if you think it's not periodic, raise your hand. Anyone? Okay. Yeah, and yeah, indeed it's not periodic. And this is quite obvious just because the thing is not singular. Okay. So we talked at last class, just the previous class today, we said that, so let's try to jump back around here, I think. Yeah, we say that for periodic signal, you will get the linear combination of a whole bunch of impulse train. Okay, so for periodic signal, the Fourier transform should look like zeros should be 0 everywhere instead, but just a whole bunch of spikes. But the signal we see here, okay, sorry, too much. It should be here. Okay, the signal we see here is it has no spikes, and it has those non-zero component, non-zero finite values. So this is totally not a periodic signal, not a spectrum of periodic signal. It's a spectrum of some aperiodic signal. Okay, so x of n is not periodic, and then the next question is, now this is harder. Do you think x of big X? I guess that's yeah. So do you think big X is a real signal? Okay. So if you think this is a real signal, sorry, wrong question. So big X look like this. So do you think small x of n is a real signal? Okay. So if you think a small x n is a real signal, raise your hand. And if you think it's not a real signal, raise your hand. Okay. So one thing is not real. And here this is well, this is a hard calculation question. So basically you need to check that big X of e to j omega equal to x star. So basically x star of e to j omega equal to x over e to minus j omega, or x over e to j omega equal to x star of e to minus j omega. So think if you take a complex conjugation and change the location of change the sign of omega, it gives you the same signal. And as a function of omega, that's indeed true. Okay, so because you change the because if you change do the complex conjugation, then the amplitude doesn't change, and and then the amplitude doesn't change, and you change omega to minus omega, this doesn't change, and so that check out. And also on the angle, when you do complex conjugation, the slope will flip up and down, so it becomes a negative slope. And but then you flip, you get a minus sign omega, you flip left and right, so you will flip back to the same slope. Okay, so you see that you do complex conjugation, and at the minus sign omega, your big X is amplitude, and the angle doesn't change. So X of n is actually real. And you can also check with something that we talked about in chapter 4, that you can check the even and odd of your amplitude and the angle directly. And in chapter 4, we say that if a signal is real, then the amplitude will be an even function, and the angle will be odd function. Okay, and indeed that's true. So the angle here is odd function, and the amplitude here is even function. Okay. And so big X is so small x is actually a real function. Okay, and and next question is X of n even function? Okay, so you think X of n is an even function, raise your hand. And okay, so some people, and they think X of n is not an even function, raise your hand. No one? People are better at guessing today. Okay, so X of n is not actually an even function. And so what's X of n is so I think even odd is actually an easier question than real or imaginary. Okay, so in the time reversal property, we say that X of n is an even function if only if big X is an even function. Okay, and from here, do we see big X is an even function? Well, its amplitude is an even function, but the angle is not an even function. And if you want to be an even function, both your amplitude and the angle should be an even function. Okay, and because the angle is not an even function, so big X is not actually an even function. So X of n is not an even function. Okay, and also another way to see this is that we have to say that we know that we already know that X of n is real, and so if X of n is real and even, then big X needs to be real and even. But big X is obviously not real because it has a non-zero angle here, non-zero angle on a lot of angles. Okay, on a lot of omega. So this is not a real function. Big X is not a real function. So X of n is not a real and even function. So it's not an even function. Okay, and finally, do you think X of n has finite energy or not finite energy? If you think it has finite energy, raise your hand. And if you think don't have finite energy, raise your hand. Okay, and so this one is easier, and indeed it has a finite energy because for energy you only care about the amplitude of this signal, and we just talk about possible relationship. We say energy of your signal is basically proportional to energy of frequency domain in one period. Okay, and frequency in energy in frequency domain in one period is related to kind of the integral in this thing, on this thing, integral of square of this thing, and this is finite everywhere, so the integral will be finite, and the integral will be finite, and you will get some finite energy in frequency domain, and you will get some finite energy in the time domain, and here we have. We claim that the integration will be this thing if you actually do the integration. Okay, but we don't ask you to do integration. You can check the integration yourself, and hopefully we say the number correct, and you actually integration this thing squared, and then divide by 2 pi, you get this 7/4. Okay, so that's the example of the property. Of some properties. Example of example of knowing properties of X of n from looking at the big X of j omega, e to j omega. Okay, And the next, we still have some time, so let's try to teach you a little more. So let's talk about convolution property. Okay, and convolution property, just like in the continuous time case, is a pretty important property because it related to LTI system. But well, the relation to LTI system story is the same. So we kind of skip here and well, we say the property here. So properties here says that y of n, if it equal to convolution between x of n and h of n, then big Y of e to the j omega will equal to the multiplication between big X of e to the j omega and the big H of e to the j omega. So we have a convolution in time domain, you will get a multiplication on the frequency domain. And just like chapter 4, this has a very nice this has a very nice interpretation in terms of LTI system, because if you think y of n is the output of your LTI system, x of n is the input of your LTI system, and h of n are the impulse response of your LTI system, then you see that in frequency domain, your big Y, your output, so your frequency domain output will be your frequency domain input just multiplied by this system function big H. And the big H will be the Fourier transform of your small h. And the big H of e to the j omega will also be the eigenvalue, so we define it as the eigenvalue of e to the j omega n. Okay. And so we see some examples. So a very basic example is this time delay system. So your h of n is delta of n minus n0. And then you try to have your output y of n as x convoluted with h. And this convolution is very easy. If you do convolution directly, you will get the end result here. This is a time delay system. This you will get x of n minus n0. Okay. So this is delta of n minus n0. You convolute it with something, you get some x, you get x of n minus n0. Okay, so we know this before, and we check that if you go to frequency domain to calculate this, it will get also be true. So first we get big H. So calculate big H, that's the Fourier transform of this delta n minus n0, and we use the brute force formula to calculate. So summation n from n to infinity plus infinity, delta of n minus n0 times e to n minus j omega n. And the delta function set n as n0, so we get e to n minus j omega n0. Okay, and so in a frequency domain, you just have big Y equal to e to the minus j omega n0 times big X of e to the j omega, and just like in a continuous time case, then you see you try to reverse Fourier transform back to inverse Fourier transform back to y of n, and you see that this is just the time shift property. Okay, time shift. This is a time shift property, and this is a time shift property, and you get that this is a Fourier transform of x over n minus n0. Okay. Okay. And that's one example of a system of a LTI system that you see that this time domain description and the frequency domain description check out. And then we have a next example that is we can now calculate the time domain description of I guess this example we also see similar thing in chapter 4. So we now can describe the time domain signal of ideal low-pass filter. So ideal low-pass filter for discrete time signal look like this. So it only passes things around signal around 0 or signal around 2 pi minus 2 pi, etc. Okay, and we do the Fourier transform of these things. So inverse Fourier transform of these things. So we have integration 1 over 2 pi, integration from minus pi to pi is h over e to the j omega, e to the j omega, and d omega. Okay. And then we see that you get this almost sinc function. So this will be integration minus omega c to omega c, e to the j omega n d omega, and this sine omega c n over pi n. Okay, and we actually already see this integration before. This was what we do in chapter 3. Okay. In chapter 3, we try to have the we try to have the Fourier series expression of this kind of periodic this block wave signal, and it was this sin k over k signal. Okay, and anyway, you can plot this as a function of n. This is now function of n, h of n, and it's this kind of like a sample sync signal, and yeah, so it has this decay of 1 over n, and it has this oscillation like sine over n. Okay, and yeah, and now we can talk about some things here. So first, note that this thing has a non-zero value for n less than 0. So so h of n has a non-zero value for n less than 0. So you see that this is not causal. And just like in the continuous time case, then we think this is not very easy to build field, not a very ideal filter to build in terms of engineering, because it's not causal, and so you need to delay your output somewhat, for example. And also interesting thing happen is you cut off this thing at some finite omega. So if you don't want to wait for if you cut off this n at some value big W minus big W to big W, and so at some finite n, and then we'll get Gibbs phenomena in your filter. Okay, this Gibbs phenomena is what we same as it has the same mass as what we talked in chapter 3, where you try to sound this back to this block wave signal, and you see that then you see that you will have ripples at the edge of those discontinuity. Okay, and yeah, so in some sense, this go back to a bit of convergence issue we talked about. So we say that the discrete Fourier transform. So when we talk about convergence, we say that usually you don't have convergence issue when you try to add back to this time domain signal, because time domain signal is discrete, you don't have ripples. But here you see that when you try to add back to the frequency domain signal, then frequency domain signal is continuous, then you can actually get Gibbs phenomena. You can have those ripples. Okay, so the convergence is a bit more tricky when you try to add back to some beta frequency domain signal. Okay, so it's quite interesting. Okay, any question on this low pass filter example? If not, then let's talk about next example. Okay, so this example is quite important, because this is what we will do when we solve a difference equation. And this example is you have well, just like in a continuous time case, we try to do the convolution of two exponential decay signals. So we have x of n equal to beta to the n u of n, and h of n equal to alpha to the n u of n. And for now, we can kind of think alpha and beta as some positive real value less than 1. So the signal is kind of this exponential decay. And then we try to have the output that's y of n equal to x of n convoluted with h of n. Okay. And yeah, as our application of convolution property, we go to frequency domain, and we have a big X and a big H, and we'll recalculate its Fourier transform on example 5.1, and this is 1 over 1 minus beta e to the minus j omega, and then big H is similar, just change beta to alpha, so it is 1 over 1 minus alpha e to the minus j omega. Oh, sorry, I have a typo here. Let me mark the typo and change it later. Okay, so this minus sign is a bit tilted, so minus sign here. Okay, and yeah. Okay, so big X and big H, and and then big Y, we can write down directly, just multiply big X and big H. So it is 1 over 1 minus alpha something, and times 1 minus beta something. Okay, and yeah, so just like chapter 4, we want to then we don't know the inverse Fourier transform of this thing, but we want to break it into the two summation of the two partial fractions. So we do partial fraction expansion to break this into 1 or something over 1 minus alpha e to the minus j omega plus something over 1 minus beta e to the minus j omega. Okay, and yeah, so basically now the x is like in terms of x it's a bit weird, but you can the x is like this e to the minus j omega. Okay, in terms of polynomial in x, but anyway. You can do partial fraction expansion to calculate your a and b here, and for some reason we write b minus b here. But anyway, you can calculate a and b, and then in terms of this alpha and beta, and you get a equal to alpha over alpha minus beta, and b equal to beta over alpha minus beta. Okay, and then with those two terms, you know it's the inverse Fourier transform, and it's this. So this inverse Fourier transform for this term is alpha to n u of n, and the inverse Fourier transform of this thing is beta to n u of n, and with coefficient minus b and a, and so here is a and minus b, and you kind of write everything together, then you see your 1 of n is 1 over alpha minus beta, everything has this term, and alpha to the n plus 1 u of n minus beta to the n plus 1 u of n. Okay. And obviously, to do this partial fraction expansion, we need to assume alpha not equal to beta here. Okay, alpha not equal to beta. Okay. Okay, so this is the easy case of the example, and just like in chapter 4, the hard case of the example is when alpha not equal to beta. Okay. So when alpha not equal to beta, you cannot partial fraction expansion to break it into two terms. So you have a fraction that's something squared. Okay, so you need to directly calculate I guess you need to have a relation that tells you what's the inverse Fourier transform of this 1 over 1 minus alpha e to the minus j omega squared. Okay. And also just like in chapter 4, so this is where you use this differential property, and in particular differential on omega property. Okay, so we see so we try to get differentiation of omega so we try to get a differentiation of omega on this thing we know to do Fourier transform, this 1 over 1 minus alpha e to the minus omega. We do differentiation, then we will get so this minus 1 will become this minus 1 power become minus 2 power, so we'll get this square, but we'll actually also get extra terms, so we'll get those extra minus alpha and the extra so we differentiate this thing with omega, we'll get extra minus 1 minus alpha, and extra e to the minus j omega, and extra minus j, and you combine all this, so you try to correct all the extra terms, you get those j over alpha and e to the j omega. Okay, I guess we should write down, we have extra terms, so let's write down all the calculation here to make sure we don't do things wrong. So dd omega, all those things, 1 minus 1 over 1 minus alpha e to the minus j omega. Let's try to do some calculus, and so it's so first we have a minus 1 from the minus 1 power, and this thing to the minus 2 power, so 1 over 1 minus alpha e to the minus j omega second power, and then this thing dd omega, and that's minus alpha, and e to the minus j omega, and then and times minus j. Okay, and so if we cancel everything, so this plus minus 1 cancel with this minus 1, and so this thing equal to minus j alpha e to the minus j omega, and those things square. Okay, and so we move all those things to the other side, all those extra factors to the other side. Then we see this big Y, which equal to this square, equal to, so minus j to other side become plus j, and alpha go to 1 over alpha, and e to the minus j omega become e to the plus j omega. Okay, and so that's the annoying calculation. And so now we have a big Y has this thing, and now we use whole bunch of property to get a small y. Okay, and the first property we use is the differential property we talk about. So we combine, I guess, so we try to, I guess, oh sorry. So here we start with our Fourier transform pair. That's this first order. The first order term, so this is 1 over 1 minus alpha e to the minus j omega. Fourier transform to alpha to the n u of n, this we know, and we put the differential property on this, and so we see dd omega of this thing. Okay, so the dd omega of this thing times j will Fourier transform to n alpha to n u of n. Okay, and okay, and but we don't get everything yet. Okay, so so we compare this thing with this thing, so we see we got a j here and dd omega thing, and so alpha is easy to deal with. You can just divide both sides by alpha, but then you also have the hr e to the j omega term. Okay, and to get hr e to the j omega term back, then we use the time shift property. Okay, because we know if we get omega, we know if we get n to n plus 1, then we will get hr j omega e to the j omega term on the frequency domain. Okay, so we change all the n to n plus 1, then you have n plus 1 alpha to n plus 1 u of n plus 1, and they will Fourier transform to e to this j e to the j omega dd omega and this thing. Okay, now you compare this to this, you see just divide by alpha by both sides, then you will get divide alpha by on both sides, then this thing will become big Y, and this thing should be your small y. Okay, so this thing divided by alpha will be your small y, so small y equal to n plus 1, alpha to n u of n plus 1. Okay, and so this is what your y of n, and you might think this is a bit weird because u of n plus 1. Okay, okay. Then you think you kind of think that the signal start n equal to minus 1, right? Because u of n plus 1 only cut off your n at n equal to minus 1. Okay, and this is a bit weird. You think this should not happen because now you think back this as a LTI signal. The x of n is starting at n equal to 0 because you cut off u of n. And h of n is h of n give you a causal excuse me, h of n is give you a causal system because it also start at n equal to 0, and then your y of n should also start at n equal to 0 because you have a causal system acting on a signal start with 0, then your output should start with n equal to 0, and that's actually check out because you check this thing at n equal to minus 1, then you see that when n equal to minus 1, then this n plus 1 term equal to 0. Okay, so at n equal to minus 1, this thing actually also equal to 0. So instead of saying cut off minus 1, you can say it's cut off 0. Okay, so y of n equal to n plus 1 and alpha to n u of n. Okay. And so this looks nicer. You would think about its interpretation as the signal starting at n equal to 0. Okay, so that's the example of getting system output with this LTI system that has exponential decay, and we'll see more of this example when we solve the difference equation. And yeah, so those are harder questions where you need to do partial fraction expansion. And and we derive the Fourier transform of the second order term with the differential property, and we see this is more involved than chapter 4 because you also need to account for this e to a j omega using this tangent property. Okay. And but in the end we get the Fourier transform of this second order term is n plus 1 alpha to the n u of n, and basically you get this extra n plus 1 term. Okay, and you can use a similar calculation to see what's the Fourier transform of the third order term, fourth order term, or higher order term. Okay. And so we actually have time. So let's try to do the next example of the convolution property and call it a day. Okay. And so the next example is this example where we try to get a bandpass filter from high pass filter and from application of a two low pass filter. Okay. So we try to see what happens if we pass your x of n through a system like this. Okay, so we copy our x of n into two copies, and the first copy will multiply by -1 to the n, and go through this low pass filter and multiply by -1 to the n, and the other part it will go through this low pass filter and just go through this low pass filter, and you add both of them back, and that's output 1 of n. And our low pass filter is like this. Okay. Sorry, I should write. So this is a bit confusing. I should use two color. Okay. This picture has too much information inside. Okay. So low pass filter is filtering all, is passing everything between -4 and pi over 4. And so it's pi, and it should repeat itself every pi. So maybe at 2 pi here, you also have a low pass here, and then negative 2 pi has a low pass here. Okay, and yeah. So low pass filter is quite obvious what it do. You will only pass through signal at low frequency. And now we want to see what happened to the upper branch of x of n. So what does this -1 to the n, then multiply by -1 to the n, then go through low pass filter, then multiply by -1 to the n do. Okay. And so we try to analyze this. So we see, so we try to analyze the higher branch with on the frequency domain. Okay. And by the tangent property, so we have talked about this property before. By the frequency shift property, we see that you multiply by -1 to the n on the time domain. What happens is you will get a shift by pi in the frequency domain. Okay, let's try to go. Let's see. Where was the property? About here. It's this property. So we say if you this property, we say although we are only applying this on filters, but we say if you multiply your signal by -1 to the n, what happens is you shift the frequency by pi. Okay, and so if you check this big omega 1 here, big W1 here, it will be the frequency, the spectrum of your input shift by pi. Okay. And then this W2, big W2 will be applying low pass filter on the will be applying low pass filter on your big X. So you have a big H, big H low pass filter on your big X shifted by pi, and then W3, where you multiply -1 to the n again, will be the output shifted by pi. The W2 shifted by pi again. Okay. And this thing should be by pi, so you see your low pass filter, this omega here should be by pi, and then your x should be by pi again, and so your x will shift by 2 pi. Big X will shift by 2 pi. But big X is a periodic function with period 2 pi, so big X shift by 2 pi is just big X. And so you see that the end result of your big W3 here is you apply your low pass filter strip by pi on your big X. Okay, and well, then then think about just like the example is here. Then this example we already talked about. We see that low pass filter strip by pi is just a high pass filter. Okay, and so what happened is that on the higher branch, what your signal experience is going through a high pass filters or filter like this. Filter center around pi or minus pi, etc. Okay, and yeah, so your W3 is your signal going through a high pass filter. That is low pass filter strip by pi, and the low branch is your signal going through a low pass filter. And so the end result of your signal is end result of this total system is you have a low pass filter. Add together with the high pass filter, then you get a band pass filter. So you'll pass through things that's very low frequency or very high frequency. Okay, and yeah, so that's some example of the convolution property. So you see that using a convolution property, you see you can express how your LTI system goes by your LTI system by how the frequency domain signal change. Your frequency domain signal get multiplied by some big H, then you that's what happened in your LTI system. Okay, and yeah, so we have some leftover time, but I think we can stop early. But yeah, let's go through a bit review. That's the convolution property, and it says that in the time domain, your LTI system is input convoluted with impulse response, and in the frequency domain, you have your output is your input times your system function, this big H. Okay, and yeah, you can go back and forth between your frequency domain and time domain to get your output signal. Okay, and yeah, and also like just like in chapter 4, this tells us to how to calculate small h from big H. You just calculate the inverse Fourier transform to on big H, then you will get your impulse response. Okay, and yeah, so I think we can stop today, and we'll continue on Thursday, and we should be able to. Hopefully, you can finish chapter 5 on Thursday. Okay, yeah. So yeah, see you on Thursday.